Ramanujan for G is now available on the Google Play Store. Try it out for free.
Hi students, so this is another class of for JnanaMarga Technologies physics class. So we are moving along with the material, and today I'm going to start a new chapter. Okay, and the chapter I'm going to start deals with related material to what we were studying before, which was we were looking at magnetostatics, right? So now in magnetostatics, one of the ideas we looked at was this idea of ferromagnetic material. That is, material like, for instance, the solenoid, where you have ferromagnetic material which is wound with a coil, right? And when there is a current pass through that coil, it induces a electromagnetic field in the ferromagnetic material, right? So that was the idea behind this solenoid. So we had an iron core surrounded by a magnetic material, and we induced a field there. Now we are going to look at the inverse. Okay, in a time varying field, if there is a coil, which is kept in a time varying field, what happens? There is a current induced. Okay, that's the idea here. Anyway, before we go there, we first have to discuss, get through our promotional material. As you know, yesterday many students took the NEET exam. It was the 2022 NEET exam, and many students have taken it, including students from who have been part of our program. If you have been in the earlier lectures, maybe you took it, right? And there is also the group that is going to be taking it in May 2022, and hopefully you are all tuned in and you're going to be listening in or to the recording. Okay, so it is for these students that we have now upgraded our Sushruta for NEET program, and we have upgraded it, and we will be upgrading it one more time to include assessment. Right now we have self-assessment, and the self-assessment is entirely aimed to help students better see how well they are doing. Okay, so after you learn a chapter, you immediately take an assessment. Okay, so that's the very goal of it all, right? So let's say you're learning electromagnetic induction, which I am teaching. You then go and read the textbook. Then along with the textbook, as you know, in our patented app, you also get, along with the textbook, you get these slides, you get the videos from IIT PAL, and then once you get the slides, you get the videos, then you are able to, say, all right, I have learned what I need to learn. You can effectively learn using our app. The last part is you can self-assess. I get an idea of how well I'm doing. So that is a very key part of our program. So Sushruta for NEET is now ready. You just have to go to Google Play and look for com.jnanamarga.sushruta. So com.jnanamarga.sushruta, you type it in there, our app will be the first that shows up. Okay. The second app is for the JEE students. Ramanujan also includes assessment. Okay, these are the lowest priced apps in the market, and these are the best ways to prepare for NEET JEE for affordability. You know, it's the most affordable, highest quality lectures, and the highest, a set of the highest quality, along with now self-assessment, helps you to go into a program which then helps you learn the material and then test yourself. Okay, so for the JEE mains, these are some of the best methods that you can use sitting in your home without going to Kota, without going to Visakhapatnam, etc. Okay, don't go anywhere. You sit at home and learn, and there is no tutor coming home and charging an arm and a leg. Okay, so now let's get going with today's material. Now, can a magnetic field produce currents? You know, Faraday, Michael Faraday, explained that this is actually possible, that a changing field, in fact, does produce currents. Okay, and so he did, several excellent experiments which go into the heart of electromagnetics, and which then laid the foundation for all that is to come after that. Today, Faraday's experiment is what puts power in your home. To say that would not be too wrong. Okay. Now, what Faraday did was he wrapped two wires around opposite sides of an iron ring. Okay. And then he passed so there was one wire, right, which was connected to a battery. Okay. And so when he switched on the battery, right, into that iron ring, or called a toroid or a torus, right, and on the other side he connected it to a galvanometer. He plugged one wire into a galvanometer and watched it as he connected the other wire to battery. Indeed, he saw what is called a transient current when he connected the wire to the other side, and when he disconnected the, now, why was it transient? Because the battery produced a steady voltage, right, and the wire had a fixed resistance, and therefore it was not changing except at the point when he switched on the battery. Okay, because what you need is a changing field, and it only changes when you switch it on. At that moment there is a change, then it becomes a steady state field. Okay, so now if you keep doing that, then you keep getting, it keeps producing, moving now. So what he was saying is that there is a current induced in the second half of the circuit. In this part of the circuit, there is a current induced by a changing field, which is what we, if you remember last class, we discussed the solenoid, right? So the solenoid, there is a magnetic flux in the solenoid, right? Or in this case, the toroid, right? Because there is a magnetic flux in the toroid, it induces a current in the second coil. Okay, this current from the battery creates the magnetic field that induces a current in the second coil, and therefore you see a flick. Okay, why does it keep not continue on? Because you need a changing field. Okay, so this induction was due to the change in magnetic flux that occurred. The battery was connected and disconnected. So you switch it on, it comes on. You pull it out, it again swings. Okay, so that's the important point there. Okay, so you switch it on, it comes, swings, and comes back to steady state. Then when you pull it off, again it swings and comes back to the steady state. Okay, so that is the idea there. Okay, moving a magnet, here a coil generates a current in the coil. Okay, moving the coil in front of a magnet also generates a current in the coil. You move the magnet or you move the coil. Okay, either causes a current. Okay, the direction of current depends on the movement towards or away. Okay, placing another coil nearby and changing the current also produces a generates a current. Okay, so these are what are called induced currents. Okay, so now look at the following case. Okay, one is the magnet moving near the coil. So as you move the magnet like with your hand, right, it produces induces a current, right? The most common case that we found was that we use in normal life is the case of the bicycle. In at least I don't know if today there are these kinds of bicycles, but when I was growing up, the bicycle used to have a dynamo, what is called a dynamo. Dynamo would be very close to the tire of the bicycle, and as the tire spun, it would spin the dynamo, and the dynamo would then have a magnet which then was spinning, and then it would then be connected to the light on the bicycle. So human generated power was producing the movement, was causing a changing magnetic field, and the changing magnetic field was inducing a current in the closed loop. Okay, and this closed current in the closed loop was then lighting the lamp in front of the cycle. Okay, so very similar to this idea. So now if you look at let's say you had this square rod, and then you had this another piece of metal which then completed the full circuit. This is a closed circuit. Then you move this metal back and forth in this magnetic field, then there is a current induced in the circuit. This is a circuit, closed circuit. You need to have a closed circuit for a current, right? So now there is what is called a EMF, okay, electromagnetic flux. So now magnetic flux is phi equals B dot dA. Okay, B dot dA is the magnetic flux. Okay, now the magnetic flux, right? If it was changing, a changing magnetic flux will then produce a EMF. Now there is another person called Lenz, Lenz. Lenz, he said that he introduced a negative sign. He said that the magnetic flux will act in such a way, the EMF will be in such a direction so as to oppose the changing flux. So whatever flux is changing, it will then reduce the change. Okay, so that is whenever a change produces an electric current, where the direction of the induced current is so as to produce effects opposing the change. Okay, the changing flux will be reduced. Okay, so that is the basic idea. So we already did this. So if you wanted to, you already know that the EMF is a closed integral of E dot dl, right? dV by dx equals E, right? So closed integral of E dot dl will equal negative d by dt of closed integral of B dot dA. Okay, so that's the idea here in deriving the what is called Faraday's and Lenz law. Okay, so d phi is the flux is B dot dA, d phi by dt equals EMF, which is the voltage. Negative d phi by dt equals. Okay, so and So now, how do we measure the magnetic flux? As you know, B, you have B, if you had an area like this, right? That area has a normal vector. The normal vector A represents a particular area. So if you had a circular area like this, there would be a vector like that. Okay. And if there was a B in a different direction, or in the same, along that A, right? So if there was a surface like this, and the B was like this, then you will have B dot dA will be positive, right? Maximum when B and A are in the same direction. Then the B dot dA will be positive. If B in, but the most important point here is that you have to kind of change the flux. Okay, so typically, how is the flux changed? Either you move the area of the coil. Okay, so if B increases with time, then d phi by dt is greater than 0. Okay, so the EMF is, so you need a changing magnetic field. Okay, a changing, which leads to a changing flux, a changing B, which changes with time. Otherwise, you need to change the A. You either change the B or you change the A. Okay, so either the area, the coil itself is moving, that is one case, or the field is moving. Okay, so now how is that done? Here, what is happening, right? Here, the field is moving because the magnet is, when you move the magnet, the field is moving. Here, the field is the same, but the area is changing, right? B dot dA is changing. Okay, so two versions. That's why they give two examples to explain that both can work. Okay, now, and both are used. Now in a generator, like we will see examples of the generator. There is the hydroelectric generator, there is the thermal power generator, there is the all of these use one form of, in the case of the hydroelectric generator, there is the power of water that rotates the like a an electromagnet. Okay, in the case of the hydroelectric, in the case of thermal power, thermal means coal-based power. Coal burns water. The water flows and produces steam. Water is, and that steam is used to, from the coal, burning of the coal, the steam is used to make the rotate the the generator. Okay, and when the generator rotates power up, it's like, you already have seen the steam engine, right? The steam engine, what does it do? It rotates, it moves the train, right? Steam engine moved the train. Like that, they then used burnt coal to produce this, converted what is chemical energy of coal into leading to thermodynamic energy, which was then used to power the engine, which then in the case of the train, it rotates the wheels. Now when you make it rotate the magnet in a you then produce a coil, you then produce a changing field, and the changing field induces a current. Okay, so those are the ideas that go into electromagnetic induction. That's why your lights are on, okay, or the fan is on, etc. Okay, so now moving magnet induces current, E equal to minus d phi by dt. Okay, and so the direction of induced current, right, is, if you go one way, right, If you have the north and the south go this way, it's one thing. If you turn the magnet around, go this way, the direction of the current will change. Okay, in one case it will go, the current will go this way, the other case it will go that way. Okay. So the changing electric field leads to the changing electromagnetic field leads to an electric field and a current being induced in a surrounding coil. Okay, so so this was Faraday's law, and Lorentz said that the direction of the current is so as to oppose the magnetic field. Okay, because the current in the coil is itself going to produce a field, and that field will oppose the existing magnetic field. Okay, so that's the idea there. Okay, so uniform magnetic field B is increasing with time, therefore dB by dt, radius of the, so there's a simple example. Okay, radius of the conducting loop is 5 centimeters. Let the resistance of the loop be 5 ohms. Okay, so the radius of the conducting loop is r, right? So what is pi r square? B times pi r square, and the B is perpendicular to the area, right? So B times A, right? So if B is the B, right, 0.04 Tesla per second, right? And therefore B times A, right, is pi r square times dV by dt, and therefore it is changing at dV by dt. Is changing at 0.04 per second, right? Pi r square times 0.04 per second. Okay, so the and therefore you end up with 0.314 millivolts, right? And if you produce an EMF of 0.314 millivolts, the resistance is 5 ohms. So 0.314 millivolts divided by 5 ohms will be the current 63 microamperes. Okay, so there you are. Okay, so now a solenoid. What is a solenoid? Solenoid is a very long. If you had a rod with n turns, right? Now the magnetic field we already looked at within the solenoid is mu naught Ni, right? We already looked at that last class, right? So now if you had if you change the radius, right? So the magnetic field is mu naught Ni. So now what is the area? It is r, so pi r square times mu naught Ni. So the total flux is pi r square times mu naught Ni. Okay, so that will produce your net total flux. Okay, so and now now the induced EMF will now what do you need to do? Right, if it is a constant B, it is not going to produce anything. Okay, so what you need to do is you need to change the mu naught Ni. The only thing that you can change that is the I, right? So you must change the current at a certain pace. When you change the current at a certain pace, you then get di by dt. Okay, so then you end up with a changing time varying flux. Okay, so mu naught Ni, therefore you end up with mu naught pi r2 square times mu naught Ni. Okay, so now why do you end up with two n's? Okay, because there are n turns. Mu naught n1i, right? A very long solenoid with n turns per unit length, right? So the magnetic field decided by turns per unit length, but then the total flux is decided by the total number of turns. Okay, so that is why you end up with the area that is being covered, this, right? The flux happens all over, right? Therefore, you end up with a induced EMF. Okay, so 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 that is a very simple example for a solenoid, the current induced in a solenoid due to a solenoid. Okay, so now the area of the solenoid is pi r squared. If you had a very long solenoid, the B is mu naught n times I, where n is the number of turns per unit length. Therefore, the flux through the conductor will be B times pi r square. Okay, so B times pi r square. B is mu naught ni, and n is the number of turns per unit length. Okay, therefore, the induced EMF is d phi by dt mu naught ni and pi r square is a, right, and therefore mu naught na di by dt. Okay, that's the induced EMF. Now, and therefore, using this, right, if you wanted to find the, the electric field, the electric field is given by E dot dl, and it is a line integral of E dot dl, so E times 2 pi r. So if you look at the electric field, E times 2 pi r, it will give you mu naught na di by dt. Okay, so so that is as far as how to go from find the corresponding electric field due to electromagnetic induction. Okay, so now the other case is is the case where the changing flux is due to motion of, like for instance, you had this, right? You had this square loop, and then you are moving this one piece back and forth, right? So what is the area being covered, right? The area being covered is dictated by how the induced the EQ, in this case the QVB is the force, right? Q times V cross B is the Lorentz force, right? And the Lorentz force, when it is set equal to EQ, right? So the Q's cancel, therefore you have E equals VB, right? Therefore, VB times L, right, by R will give you the corresponding I times L cross B, is the other way to look at it, So I times L cross B is the force. Okay, so now what we are trying to do is we are trying to determine the current induced is VBL by R, and you are adding another L times B to detect the magnetic force in the moving conductor. Okay, so what is happening here? we have a magnetic field, and the magnetic field is causing and there is a moving there is a moving charge in that magnetic field which is induced, right? So now we are looking at the value of that induced current, okay, or in this case we're trying to determine the corresponding force. Okay, so that force I times L cross B, right, is the Lorentz force, and I times L cross B, the corresponding I is the induced current. The induced current is E by R, and E is d phi by dt, right, and that is VBL. Okay, so that's how you end up with the formula in this page. Okay, so if you had what is the work done per unit time, or the power, which is the power, like power is F dot V. So we already derived F, right? V square L square V by R. So you multiply it by another V, so you'll have B square L square V square by R. Okay, and what is the corresponding? That will equal the corresponding the work done is going to lead to I square R worth of energy being consumed, right? So that's how the whole thing lines up. Okay, so so here there is a simple example. D phi by dt, therefore is B times L times dx by dt, right? Dx is what? Dx by dt is what? V, right? So B times L times V will lead to, because B times A is the flux, right? So the rate of change of flux is d, therefore, because the only thing moving is this one. This is moving at a velocity v, right? Therefore, BLV will give you the rate of change of flux. Rate of change of flux is the EMF, right? Negative BLV is the EMF. And therefore, from that you can then calculate the current. And from the current, you can then, the magnetic force on the rod is given by I times L cos B. Okay. So very simple ideas, but again, this is how it works. Now, one thing that happens is what they, sometimes these currents that are induced, they tend to waste energy. So if there are a lot of additional currents that are induced, these are called eddy currents. Like eddies are in a string, right? So they tend to waste the energy of the string. Okay. Now, similarly, these eddy currents, they waste the energy of the system. So what they do is they laminate, layer the things like transformers. In transformers, they layer things so that the paths of the eddy currents are reduced. Okay. Therefore, because the paths are reduced, they don't use up that much energy. Okay. So now here's an interesting application. There is a pendulum in a field. Okay. Now, in order to reduce the eddy currents, what they are doing is they are cutting up the pendulum into these kinds of like sawtooth pendulum, and the sawtooth pendulum, the effect of there is lesser eddy currents, therefore you have more conservation of the energy that is produced by moving the pendulum back and forth in the magnetic field. So you have a magnetic field in which you're moving the pendulum. So you have an induced current, and that induced current is reduced due to the effect of the eddy currents. Okay, so eddy currents is used in magnetic braking in trains, in electric motors, and of course in transformers, induction furnace, etc. And it is in order to reduce the heating that happens in transformers, we laminate the core. So understanding eddy currents is used in several of these areas. Okay. Now there are two types of inductance. Okay, what is inductance? Inductance happens when you have you have the classical case of the transformer, right? So now you have two sides, right? You have the flux, which is caused by one current, right, which then leads to you have one current on one side, which then causes a magnetic field, which then induces the current on the other side, right? So that is the traditional case of where inductance is used. Now, the flux that is induced, right? There is this thing called mutual inductance, M, right? Now, the flux that is generated is proportional to the current in the other on the other side. Okay, and the mutual inductance is a constant of proportionality which relates the current on the other side to the flux produced on one side. So phi 2 equals M21 times I1. So there is a current here on I1. There is a mutual inductance between the two sides, and the flux on the other side is proportional to the flux through loop 2 is proportional to the current in loop 1. And how the two are related is said to be using this constant N, which is called mutual inductance. So let's reiterate what's going on. There is a current in this loop. Okay, it is now inducing a current in the other loop. Okay. Okay. So there are two cases. One is mutual inductance when there are two loops. Okay, so now the first loop has a current which induces a magnetic field and then causes a current in the second loop, right? So what is the relationship between the flux in this that goes through the second loop and the current in the first loop? That is the relationship is called the constant. The two are proportional, right? Clearly proportional. So the more the current, the more the flux, right? So the constant that relates the two is said to be mutual inductance. Of course, these are we are no longer in the realm of strict. How can I put it? We are no longer looking at either Faraday's law or its associated Maxwell's equation, right? We are roughly looking at these things from at a higher level, and we are relating the two in the context of practical application. Okay, and a lot of electromagnetics they do look at the field generated, etc. But finally, it comes down to this. Okay, they do try to improve a transformer. They do try to improve the generator. You always want to generate or make you as much power as you want, right? And therefore, they pass the current I1 through S1. The magnetic field produced by S1 is mu naught N1 I1. The magnetic flux through each loop of S2 is now the B times pi R1 square, right? Therefore, the B times pi R1 square produces the flux, right? And that flux, right? Now you therefore have a relationship which then gives you a value for that mutual inductance, mu naught N1 N2 times pi R1 square L. Okay, so that gives you the flux, and we already looked at how this equation is derived. Mu naught Ni equals B, right? And B times A is flux. Rate of change of flux gives you, the flux is there, and we don't deal with the rate of change of flux here. We just deal with remove the I out, and everything else is the M, right? So that's all there is here. Okay, so here is two long solenoids. Okay, so there is an inner loop which is wound and an outer loop which is also wound. Okay, so now you pass a changing current in one, it produces a changing flux in the other, right? So this is the classic case of the transformer. Okay, the transformer also, they wind it, and there is a one loop and there is a second loop. You pass the current through the first loop, the second loop receives a voltage. The ratio of these loops, the ratio of the number of coils, is then proportional to the change in the whether it's a step up or a step down transformer. Okay, so these ideas, right? So with respect to the mutual inductance, basically the mutual inductance M12 will equal the mutual inductance on the other one M21. Okay, so why is that? Now that is because of the way this is derived, right? Mu naught Ni is B, right? Now B times pi r square gives gives phi, right? Now, but then the phi is, now we now turn to the other coil, right? So there are n turns, right? N2 turns per unit length in the other coil times L, right? So that is the total flux that goes through that coil. Okay, the area is the same, right? Therefore, that is the total flux that goes through a length L of solenoid 2. Okay, and now you reevaluate that, you will end up with mu naught N2. If you keep the current the same, Mn2 I2 or I2 equals I1, right? The current anyway drops out in the end. Mu naught N2 times pi R1 square, R1 and R2 are the same, multiplied by N1 times L. Okay, so you end up with the same constant, therefore you have M12 equals M21, pretty much. Okay, and therefore, that is the basic idea there, and therefore they just say mu naught Mi. Okay, and the current through the solenoid, so and the mutual inductances are the same. I induce in you, you induce in me. The two ends are pretty much the same. So M is mu naught N1 N2 times pi r square L. Okay, so so that is the mutual. Phi equals Mi is the basic idea there. Okay, now a self-inductance happens when there is just one coil. So each of the loops, so there are a number of turns, and so you then have mu naught N square pi r square L. Okay, so there is only one coil, and then it induces the current in itself. Okay, so there is a self-inductance. Okay, and and the and which is what we have this thing called the inductor coil, right? Now an inductor is the counter of the capacitor, right? Q is equal to CV dq by dt equals C times dV by dt, right? That is the equation for the capacitor, right? Now phi equals Li d phi by dt, right, is equal to E, right? So V equals L di by dt. Okay. In one case you have I equals C dV by dt. The other case you have V equals L di by dt. Okay. So one is the complement of the other. So in many cases they include an inductance and a capacitance, and they play complementing roles in circuits. So that's where we are headed next. I think I've covered quite a bit of material today, and I am therefore going to try and pause a little bit here, and I will pause with this slide before I go on to discussing phi equals Li and discussing this idea called inductance. So I will introduce inductance in the next class, and along with this idea of phi equals Li and d phi by dt equals L di by dt, right? I will then, which is equal to the EMF, V equals L di by dt, right? So along with that, I will then, look at we will then segue pretty soon into alternating current circuits, which involves R, L, and C. Okay, this L is a very critical term in looking at inductors. Okay? The self-inductance, right? So we look at that. We look at inductors, but also we will look at the transformer, in the context of electromagnetic induction. So the idea is that before I go, I want to leave an important takeaway. Okay, this is at almost the heart of what electricity and magnetism heads towards. We looked at I times L cross B, and then we looked at Ampere's law, and then we looked at the idea of the motor. Here we are looking at the generator side, and then we are looking at all these LCR circuits in a very short period of time between, say, less than 100 years. All this developed. The rapid rate at which the ideas around the electric field and the use of electricity grew, right, has been a cornerstone of modern civilization. The last 120 years or so, ever since Edison and Tesla, right, these have been fundamental to people's understanding of electricity, and it has transformed our lives in so many different ways. So with that, I'm going to bring this lecture to a close. What I suggest, though, is that students download our app, download our app based on whether they are NEET students or JEE students, Sushruta for NEET, Ramanujan for JEE, and then attempt some problems. Okay, learn the material one more time. Look at the IIT PAL lectures. All the slides that we have, these are all from the IIT PAL lectures. So I try to provide a little bit of a introduction to these IIT PAL lectures, but really you should be spending time doing the app and then reading your textbook. So if you read the textbook, look at the IIT PAL lectures, then you go and solve your problems. Look at the slides, the slide decks that we provide along with it, and and then you go and then listen one more time to the IIT PAL lectures using the slides. Then you go and attempt some questions. Then you will really have an appreciation of the material, and along with the material, the type of questions that they do ask in these tough exams like Sushruta and NEET. Okay? With that, I'm going to stop today's lecture. I have reiterated the methodology also today on how students are to study, and you have to get with the program. You have to get with, if you are with us, you have to get with our program. You have to, if you're going to some other school, they will also tell you get with the program. Fit JE, whoever it is, So you have to follow the regime that is being required from you, and then when you do that, that will set you up to really succeed in these exams, because they're not that easy. And whether you and there are many exams, that you can take BITSAT, you can take VIT exam, many different exams. Amrita University, we have a relationship with them, and they have offered us some seats as well. So very important that students do these questions and then be able to solve actual questions by attempting them from our self-assessment. All right. So with that, I'm going to end today's lecture, and I'll see you all again next class.